We often picture electricity as a smooth, continuous stream, but at the physical level, that concept of perfect flow is completely inaccurate. Take a lightning strike. This is one of the most raw, natural occurrences of electric charges moving from the clouds to the Earth. This atmospheric discharge is violent, disastrous, and completely erratic. The movement of charge here is anything but steady. We usually contrast that extreme violence with the idealized concept of perfectly uniform movement, much like water traveling calmly down a river. A standard cell-driven clock relies entirely on this controlled, steady transit of charge to keep time. Yet, despite the massive difference in scale and behavior, the erratic lightning strike and the predictable clock are governed by the exact same physical rules. To understand how a single rule governs both a natural disaster and a household item, we must redefine what moving electricity actually means at a strict mathematical level. Let's strip away the outside of a standard wire and look directly at the microscopic interior of a solid metallic conductor. Without an external field, the solid structure consists of fixed positive ions. Between them, free electrons are in constant motion due to inherent thermal energy. These electrons collide continuously with the fixed ions. After every collision, the direction of an electron's velocity is completely random. Because there is no preferential direction for these velocities, at any given moment, the exact number of electrons traveling to the left is equal to the number traveling to the right. All this chaotic thermal movement cancels itself out. On average, the net electric current in this state is exactly zero. Microscopic motion alone does not equal electrical power. An electric current requires a directed, quantifiable organization of that chaos. We cannot track a single erratic electron bouncing its way from one end of a wire to the other. We need a different way to measure this directed movement. The solution is to establish a geometric boundary. We imagine a small cross-sectional plane held normal, or perpendicular, to the direction the charges are flowing. We only care about the particles that physically cross this specific invisible counting gate. First, we calculate the net amount of positive charge that flows across the area in the forward direction. We denote this variable as Q+. Next, we account for the net amount of negative charge flowing across the area in that exact same forward direction. This is Q-. By subtracting the backward-moving negative charges from the forward-moving positive ones, we combine these vectors. This basic equation calculates the definitive net amount of charge passing our plane, represented simply as Q. Finally, we must measure this crossing over a specific time interval, which we denote as T. Current is not a measure of a particle's physical speed. It is a strict geometric accounting of net charge crossing a spatial boundary over a specific period of time. We can apply this boundary accounting first to a perfectly steady artificial system. Imagine a flow of charge that is perfectly constant and unwavering, moving forward at an even, predictable rate. The resulting mathematical quotient for this state is simply the net charge Q divided by the time interval T. This ratio defines the steady current, denoted by the capital letter I. When the flow is perfectly constant, this simple algebraic division gives us the exact current across the area in the forward direction. If this quotient turns out to be a negative number, it simply implies the net current is moving backward. Algebraic definitions like I equals Q over T are mathematically sound, but they are only reliable tools for highly idealized constant states, like that battery-powered clock. But what happens when the physical universe refuses to behave steadily? In natural events like a lightning discharge, the flow of charge is intensely erratic. Taking a simple average over a long time interval provides a uselessly inaccurate number. This is a Cartesian graph plotting charge on the y-axis against time on the x-axis. A steady direct current, or DC, appears as a straight, linear slope. But the reality of a dynamic, surging flow of charge maps out as a highly curved exponential line. If we define a specific block of time, delta t, we can calculate the total change in charge, delta q, across that wide window. However, to find the true instantaneous current at one specific moment, we cannot use a wide time block. We have to shrink the interval. We apply the mathematical concept of a limit. As the time interval, delta t, approaches zero, our measurement narrows down to a single point. This gives us the formal, calculus-based definition of electric current. This equation states that current at time t is the value of the ratio of delta Q to delta T, evaluated in the extreme limit where delta T tends exactly to 0. When natural charge flow is chaotic, we must abandon simple averages. The differential limit is required to capture the exact mathematical reality of a single instant in time. We translate this theoretical mathematics into the physical world, using the standard SI unit of current, the ampere. The ampere is formally defined through the magnetic effects of currents, a mechanism we will explore in future lessons. Let's apply this unit to the massive scale of atmospheric discharge we looked at earlier. An average lightning bolt carries currents on the order of tens of thousands of amperes. Scaling down, we look at the power grids that maintain our daily infrastructure. To minimize power loss over long distances, these massive cables carry energy at enormous voltages, which a transformer then steps down for safe use in our homes. Inside the home, a standard device operating on steady current looks very different. Domestic appliances like this typically operate in the single digits, drawing roughly 1 to 3 amperes of current. Finally, we scale down to the microscopic extreme, deep inside the human body, where electric charges in our nerves operate in mere microamperes. All three of these completely different phenomena are united by that single physical law. The ampere serves as a universal, scale-invariant metric of charge transfer. It governs the physical world with absolute consistency, from the destructive energy of the cosmos to the electrical impulses of the human brain.